Okay. Share screen. Okay, one thing to check. Can you see the hand moving around on the screen? Get a yes or a no. If you don't see anything, let me know. There should be a hand moving around. No, okay, that's too bad. Okay, I thought I had that worked out. Okay, but you do see the screen, right? Yes, good. Okay, let's get started. Okay, so let's just take a step back and remember what we're doing. So our goal now don't tell me. I just checked my pen. It was working just fine. Okay, good. So our goal is to understand the behavior of highly overparameterized networks. Networks. Remember, overparameterized means we have far more parameters to fit than we do training examples. And the hope, oops, and the reason we're doing this, so the hope really, what's going on? So I have that fixed as well. Oh. So the hope, I do not know why my pen stops working. Okay. There we go. So the hope is that will tell us something about the brain. And the way that, and basically the brain is also highly overparameterized. Now, brains, and we're looking at artificial networks. Artificial networks are very different from the brain. So really what we need to do is our strategy is to extract general principles or extract some kind of principles. Because overparameterized systems are fundamentally different than sort of the kind of problems we work in statistics where we have lots and lots of training data and not many examples. They really are fundamentally different objects. And so far, our main tool has been linear regression. Which, given the era of deep networks, seems like it might not be such a good idea. But it turns out that we can get a lot of intuition for from linear regression, and so shortly we'll soon go to nonlinear networks. And some of the intuition carries over immediately. Others we have to do a little bit of work, but what we learn from linear regression is going to be surprisingly useful for understanding nonlinear networks. Okay, so let's sort of recap what we've been doing. Remember, we have training data. So x mu, y mu, mu equals 1. So we have pre-training examples, and then we want to fit a model. So y equals w dot x equals a sum I equals 1 to n of wi xi. And n is greater than p. So n. So that's important. Usually we have n less than p. Usually we have, so the usual case is we have a large number of data. So the usual case for like 1D. Let's say we're fitting y equals wx, the one-dimensional problem. So we have x and y, and we have data points, lesser data points, and we can now, it's kind of easy to fit a line through it. Okay, so fitting a line through it is not so hard. And you can imagine that it's kind of crazy to think that in less than p. So in the simple 1D case, so first we could have like n equals. So here in this case, n equals 1. This is for n equals 1. What is going on? If you had a single point here, it'd be pretty hard to fit a line. Okay, if we only have one data point. Sorry, my pen is not behaving. There you go. Don't tell me. Shoot. This pen is not behaving at all. Okay, I think I fixed it. So it's kind of obvious, right? If you have one data point, if this is our only data point, one data point, there's no way we can fit a line through this. Okay, so the overparameterized system really seems like a kind of a strange thing to consider. But we can do it anyway. It's in 1D, it doesn't work very well. In high dimension, it does. And remember what we found So found that when we did that, so we found that our model, so our estimate of the weight, which we'll call W hat, was equal to W naught, the initial weight, plus the sum on mu nu, sum of our training examples of x mu dot x nu. This is a matrix inverse with respect to the indices x mu and nu times y nu minus W naught dot x nu. And so this is a sum. So the mu nu, this is sum over training examples over training examples. Okay, so I'm going to try to cast this in a sort of a more easy to understand form. I'm going to write this as W naught, that's the first term, minus the sum on mu comma nu of x mu dot x nu inverse x nu dot W naught, plus the sum on mu comma nu of x mu dot x nu inverse x nu, times y nu. And finally, I'm going to assume, so let's say that the true value of W star, so let W star sorry, did not know what's up with my pen today. Been working earlier. So W star equals the true weight, which means Y nu equals W star dot x nu. Okay. So the training examples are generated from a true set of weights. And what that means is this term here we can rewrite as the sum on mu comma nu of x mu times x mu dot x nu inverse x nu dot W star. Okay, so in both cases we have this kind of this matrix, and this matrix I'm going to call it P parallel equals the sum on mu nu of x mu dot x nu inverse x nu, and this is a projection operator. So if P parallel dot x alpha equals the sum on mu comma nu of x mu dot x nu inverse x nu dot alpha dot x alpha, And when we sum this on nu, this is an inverse of matrix times a matrix. This equals the identity in this space. So this sum on mu is, so this is equal to sum on mu of x mu, the identity, which is delta mu alpha, which equals x alpha. So P parallel operating on any vector inside the space spanned by the data just brings that back out. Okay. And oops. Yeah. 3. Okay. And P pen is very problematic. So P parallel dot x equals 0 if x dot x mu equals 0 for all mu. Okay. If basically x doesn't lie in the data space, it's going to be, which is quite strange. Oh, I know what happened. There we go. So P parallel dot x is 0 if x doesn't lie in the data space. So it's a projection operator. And it basically picks out data inside the space. And so we can rewrite this as W hat. Our estimate is equal to I identity matrix in the full space minus P parallel dot W naught. Our initial weight plus P parallel dot W star. And we can rewrite that as I minus P parallel dot W naught plus or minus I minus P parallel dot W star plus W star. So rewriting things. So this is W star so W hat is equal W star plus I minus P parallel dot W naught minus W star. Okay. So this is a super, super, super important result. Okay, so this is subspace spanned by the data. I may have to switch to a different pen. Subspace spanned by the data. Remember by the x mu. So the data is our x mu's, our set of x mu, right? And basically, the weights can only be updated in space spanned by the data. And this, of course, is the identity in the full space. This is identity matrix in the full space. Okay. And this is super important. So let's consider the 2D case, and let's say our data kind of lives here. Our data kind of lives here. Which I'll just draw as okay. I'm going to have to switch devices. This pen is just not working. Well, I'll finish this page. So the data looks like this, okay? 2D. And let's say, so if that's the case, so now, so the first observation, which we talked about last time, is that if we're going to fit pretty well, the data has to live in some, we only have P data points. So to fit well, the data well, so the data must live okay, I'm gonna have to switch devices. This is not working. So I'll finish this thought. Well, I'm just gonna switch devices. Sorry, guys. I'm not doing this. But I'll be able to save these notes. Uh-oh. Okay, we're connected. Meeting.
Recording in progress.
Okay. So you guys are all here, right? Yes. Share content, whiteboard. Okay, sorry about that. Okay, so where were we? So we have our W hat, our estimate is equal to W star, the true weights, plus this projection operator, I minus I minus a projection operator, call it P parallel, dot W naught minus W star. Okay. And, you know, having analytic expressions is really useful because we can figure out exactly what's going on. So let's take our axes. Let's say our data is X space. And let's say our data lives here. So these are our training examples. So each point is an x mu. Okay, so each of these points is different x mu. And so remember what we found from last time is so W hat's going to be a good approximation, fit the data well. W hat is approximately equal to W star if data lives in a low dimensional subspace okay. And low dimensional here means, you know, less than P, or maybe much less than P. We only have P training examples. Our P training examples can only live in a P dimensional space. So basically low means, let's be a little bit more clear. So low equals much less than P. Okay, our data can always only live in a P-dimensional space. So, so our training examples live in a P-dimensional space. If the data lives in a much higher dimensional space, we won't explore it. And we can see this from here. So, but that's the other thing we need. The other thing we need is that too, W star also needs to live in the low dimensional space. In the same low dimensional space. The same low dimensional space as the data. Okay. And so for instance, so this is a case, so if this training example looks like this, if W star, so if this is W star, everything's fine, right? We have, you know, we can look at the data, we'll get a pretty good estimate, everything will work out okay. If on the other hand, W star looks like this, so the green W star, that's good. If on the other hand, the W star looks like this, the red W star is bad. And the reason is that that most of, so, and the reason is that W star, for most training examples, W star dot x mu is approximately equal to 0. Right? Most training examples live out here. You know, some of them will live in here, but most live out here where basically W star dot x mu is almost perpendicular. So, you know, if this is a data point, this data point is perpendicular, nearly perpendicular to W star. And what that means, and that implies that P parallel dot W star, remember, equals the sum on mu, comma nu of x mu dot x nu inverse x nu dot W star. This is approximately equal to 0 as well. Okay. Need some more space here. Which implies that I minus P parallel dot W star is approximately equal to W star. Okay. If you go look at back up here, we're kind of running out of room. So this in turn here, oops. So this implies that W hat is equal to W star, approximately equal to W star plus I minus P parallel dot W naught. And now, because I minus P parallel dot W star is about equal to W star, we just subtract off the minus W star equals I minus P parallel dot W naught. So basically our estimate has nothing at all to do with a 2W star. Now this is approximately equal to, we get some information, but not that much. Okay. So we need two things if we're going to fit the data very well. The data has to lie on some low dimensional subspace, and that has to be the relevant subspace. Also, you can work out, so W naught should also lie in the, it's also useful for W naught to lie in this relevant subspace, because then this gets killed and that's 0 as well, which we want. So the third thing, kind of running out of room. So 3 is that W naught lies in the low D subspace. Okay, and that ensures that I minus P parallel dot W naught is approximately equal to 0. Okay, because if it lives totally in this, remember, if it lives totally in the low D subspace, then P parallel W naught is exactly equal to 0. So this is called, so remember, let's go back to our picture. Here's our picture. So what we want, this is our data. So we want W star to live in here approximately, and W naught to live in here. Okay. So this is the good case. This is, so W star lives, so we have, this basically satisfies our three things in previous slides. So this is good. So the good means the data lives in low-D subspace, okay? W star lives in a low-D subspace, and so does W naught. And that's sort of really quickly to summarize these because I want them all in one place. One, data lives in low-D subspace. Two, W star lives in low-D subspace in the same low-D subspace. And three, W naught lives in the same low-D subspace. Okay, so data is some low-D subspace status. The data lives in, and W star and W naught lives in. Okay, so this is kind of interesting because number one, the statement about the data. These things are statements about the network. Okay. So this says, in some sense, the data has to be matched to the network, or the network has to be matched to the data. And the network is really, so this is, networks all have inductive biases, okay? So it's a pretty horrible phrase, but it means something that's kind of intuitive. And that is, different networks work well on different data, okay? And what I'm going to do now is consider nonlinear regression. The chats. Okay. So linear regression, of course, is just one way to model the data. What I'm going to consider now is a deep network, and deep networks, the same ideas apply. Except, what we mean by the data changes, and exactly because it's nonlinear, sort of making sense of these things can be a little more complicated. But I'm going to start off with an example in which the exact same considerations apply, but by using a different network, we've modified the space the data lives in. Okay, so that's the plan now. So I'm going to now switch to deep networks. So deep networks are pretty common these days. They're what's ruining our lives because they're way too powerful. We've all seen ChatGPT. But they're pretty simple devices. So I'm going to do a vanilla. I'm going to start with, so I'm going to consider vanilla feed-forward networks. Okay, and these, they look like this. They have, you've probably seen pictures like this a million times. You can have different number of neurons and different layers. And in the output layer, we'll consider a single output, but if you want, you can even have multiple outputs. So and these things are connected like this. This is the input data X. So X, we'll say, lives here. So this is actually, so X lives in the first layer, and we can call this, so this is layer 1. And as we go up, we have maybe lots of different layers, and this is layer L. And then the output, it's just a scalar output. And you can actually have multiple, in principle, you can have multiple outputs. You very often do, but we're going to consider, for simplicity, we'll assume there's a single output. Okay. And so what does each layer look like? In sort of a simpler case, X, the activity in layer L is some nonlinear function. Often it's just threshold linear. W L dot X L minus 1. Okay, sometimes people put in a bias plus B. I'm going to ignore that just for simplicity. You need them in real networks, but we're going to ignore it. You can set one of the xi's to 1 if you want to get a bias. Oops. Okay, and in terms of sort of an index xi is equal to phi of the sum on j of w I j, the weight to layer L, xj, and layer L minus 1. Okay, so basically what you do for any one of these units is you sum up all its inputs. You look at this neuron, you sum up all its inputs weighted by, oops. Weighted by these weights, W. You pass them through a nonlinearity. Typically, these days, phi equals ReLU, which basically just means phi of x is a function of x. It's a 0, goes like that. But it doesn't matter. You can use almost any nonlinearity. Turns out nonlinearity matters for how well you fit these things, but it's really, the power comes from the fact that you have lots and lots of parameters. Okay, so j equals 1, the number of units in layer L. So the number of parameters is equal to the sum on L, equals 1 to L of NL. And in typical networks, it ranges, but you can easily have, 10 to the 7th, 10 to the 8th, even 10 to the 9th parameters. Some of these modern networks have actually, they're approaching brain scale. So some of them have on the order of 1 trillion. Some of these large transfer models have 10 to the 12th. Yeah, on the order of 10 to the 12th parameters. So we're approaching the number of parameters we have in the brain, and they don't typically, P, number of training examples, so parameters, and these are very often run in a regime where number of parameters, so typical networks, call this going to be equal n. So typically, n is much greater than p. You have far more parameters. You have training examples. We saw it seems like a bad idea, but we saw that it just doesn't. That it doesn't really matter. Okay. So information propagates, starts here, it propagates through here, through here, through here. Eventually, the output, the very last layer. So y we'll call this as f of x is some nonlinearity phi of w. This is now just a vector L plus 1 dot phi of w L dot x L minus 1. And then, so then xl minus 1 is expressed in terms of xl minus 2, and so on. And so this is just some function. Actually, let's write it as, so y equals some function of the weights, all the weights, which you put in sort of a giant matrix, and x, and it equals this, okay? And then to get all the way down to the input, you have to cascade it one layer at a time through this thing, okay? So this is our model. And, you know, in the old days, so this is much more powerful than, so much more powerful and y equals w dot x, right? But the power comes, the problem is, of course, these things are very hard to analyze. But we are going to analyze them in something called the Neural Tangent Kernel regime. And then once we understand that, which will be easy since we've already understood linear analysis, we'll actually talk about what happens for nonlinear networks. So about halfway through, let's take a 5-minute break. I'll be here if you have any questions, and then we'll talk about nonlinear networks. Okay, so let's go back to our problem. We have y equals f of w dot x. And I'm going to do something that may seem kind of crazy. I'm going to Taylor expand. It's approximately equal to f of w naught comma x plus w minus w naught dot partial of f of w naught comma x with respect to w naught. So this is, well, actually we can let's dot. So you can Taylor expand. If you go to all orders, this will be more or less exact. But we're going to do something that seems crazy. We're going to approximate like this by a first order term. I'm going to call this delta w. So this is delta w dot partial w naught f of w naught comma x. I'm going to give this a name. This is, I shouldn't use phi. We'll use psi of x. Depends on w naught, what else to press that? Psi of s. It turns out that, well, okay, so what do we have? We have y, our model is y equals f of w naught comma x plus delta w dot psi of x. Okay, so this is cool. This is linear regression. So we've turned our complicated deep network into a linear regression problem. And it turns out it's a good approximation for wide networks with weights initialized to, well, let's just write one number down. I'll say what this means in a second. So this is sort of strong weights and not too many training examples. Okay. What do I mean by weight initialized to 1 over n? Remember, part of our we had xi in layer L equals phi of the sum on J of wij in layer L, xj in layer L minus 1. Initialized basically initially wijl, so j equals 1 to n. Wijl is pulled from normal distribution with mean 0 and variance 1/NL. Okay, which basically means Wijl is equal to 1/√NL times squiggle IJL, and squiggle IJL is 0 mean unit variance Gaussian random variable. And this is actually pretty typical initialization in neural networks. You remember from last lecture that if Wij has this form and it's random, then this quantity here is sort of order 1. So it makes things come out the right size. It allows you to propagate information through the network. And this is known as a neural tangent kernel regime. So this is a neural tangent kernel regime. It was introduced about 3, 4, 5 years ago. Initially, people were really excited because it's linear regression, so we can analyze it. But it doesn't, and its performance is not bad. I mean, you can run this on something like MNIST, handwritten recognition, or even you can even run it on object recognition, and it does an okay job. And I'll tell you why in a second. But it's linear regression, so that means we know all about it. So let's rewrite this linear regression problem. So we have our model is y equals f of w naught comma x plus delta w dot phi of x. Okay, and we train on x mu, y mu. U equals 1 p. And so we want to our weights, choose weights. To minimize loss, which is L is 1/2 the sum on mu of y mu minus f of w naught comma x mu minus delta w dot phi of x mu. Okay, squared. Now that should be compared with linear regression. What was linear regression? Linear regression was L equals 1/2 the sum of mu y mu minus w naught dot x mu minus w dot x mu. So basically what happens is our w is now called delta w, our x mu is a nonlinear function of our input, and w naught dot x mu is basically replaced by f. Okay, otherwise it's exactly analogous. And what we've done is, here is basically we've projected our data into high dimensional space. We projected data into high dimensional space. And importantly, the projection was nonlinear. So if you linear project data, it doesn't do anything to it. This is a nonlinear projection. And it can be very nonlinear. And sort of the classical picture people paint of this is, well, so first of all, doing that makes things sometimes easy to linearly separate. Okay, this is now we basically projected into high dimensional space, and now we're trying to use a linear readout. And the picture that people often write looks something like this. Let's say we have some data in 2 dimensions, and we're trying to classify it. So we have red data points here, live in the low dimensional space, and we have blue data points here. It goes around here. Okay. And we can't, if we try to find a plane to fit through this, there's no way, right? There's no plane that classifies these data, right? We can put it here, and we can say everybody on this side is red, classifies the red on well, but everything on this side is blue. It does a pretty bad job, right? It classifies all sorts of things as red. So we can't classify data with linear regression. So we're doing classification, but all these things apply to, well, it's actually not so much with a linear function. But now suppose we projection in high dimensions. So we said phi of x equals so phi is a vector. Actually, sorry, it's a vector. It has two components. One component is just x, and the other component is absolute value of x squared. So projecting it now into a 3D space. So this is 3D. And now what happens, right? So I don't know if I'll be able to draw this. I'll try. So we have, and now what happens is the red points sort of, they form kind of a bowl shape, and the blue points, live up here. I hope you can imagine these things. They're kind of a really bad artist. But the point is, the blue ones are above so the blue points, so above the red points. Okay. And now we can take some surface, some surface that goes through here. The surface is, so the blue points above the surface, and the red points are below the surface, Okay, and now we can classify them perfectly. Okay, horribly bad drawing, but you get the idea. This nonlinear transformation that lifts and made the blue ones get lifted up higher than the red ones now allows you to fit the data perfectly. So, and again, sort of the network, this transformation, this phi, had to be in some sense matched to the data, right? If the data was drew the red and blue points differently, we would have wanted a different phi. Okay, so in this case, really what happens is the phi, the network you choose is going to be a good network, is going to make these points sort of, well, say exactly what we mean by what we want the network to make these points do. Okay, Anyhow, it's linear regression, so we can immediately write down the answer. Okay, so we're doing, so our model, remember, is y equals f of w naught comma x plus delta w dot phi of x. And so immediately we can write delta w hat. And that equals, let me, it takes a little bit of thinking. Y equals, we have f of so delta w hat is is the sum on mu and nu of phi of x mu, and then we have phi of x mu dot phi of x nu inverse times y nu minus f of w naught comma x. Okay, so it's a little bit different than what we had before. But we can actually, so we can now write y equals f of w naught comma x plus delta w dot phi of x. So it's a sum on mu nu of phi of x dot phi of x mu dot phi of x mu dot here phi of x mu dot phi of x nu inverse times y nu minus f, this is a nu, of w naught x nu. Okay, and we can actually see what happens when again, you can easily check if phi of x equals phi of x alpha, then we get y. This is just a sanity check. Y equals f of w naught x alpha plus the sum on mu nu of phi of x alpha dot phi of x mu. So phi of x mu dot phi of x nu. Don't know what I wrote here. This is phi. Inverse y nu minus f of w naught x nu. So this again, when we sum on mu, this term here is just delta alpha mu. We sum on mu, this recovers alpha, and we get equals f of w naught comma x alpha plus y alpha minus f of w naught. So we found the right weights. Again, we have this projection operator that projects us into high-dimensional space, or into the subspace, and we have the exact same considerations, okay? Except now, our data, rather than giving by x, so what do we need, right? We can actually go back to I write those down. So remember this, W and W star, this isn't the right page. These three things. So data lives in low dimensional space, and the true weights and sort of the initial weights live in the same low D space. So how does that play out in kernel regression? What we need is for this to work is that, so we're going to actually again write, so we're going to write that delta W, true delta W, the true delta W equals delta W star, which means that Y new equals delta W star dot phi of X new. Okay, that's what it means for you to model. You assume it's in the model class. And what that allows us to write is, if we just go back and look at this expression, we're going to replace Y new by phi of X new dot delta W star. Okay. And that gives us following expression. Again, so Y equals F of W naught comma X. Then we actually might as well subtract this off. So that's the sum on mu comma nu of X mu. Oops. Phi of X mu of phi of X dot phi of X mu phi of X mu dot phi of X nu inverse F of W naught comma X nu. And then the important piece is plus the sum on mu nu of phi of X mu phi of X mu dot phi of X nu inverse phi of X nu, and all this thing is dotted into delta W star. Okay, so again, if our data, this is again a projection operator. It's the identity matrix if delta W star is proportional to phi of X nu, or lies in the subspace spanned by these. So again, what we need, except now we're in phi space. So this is phi space. Our data better lie in low dimensions. Okay. The data must lie okay. Otherwise, we're going to do a bad job. Otherwise, as we saw, delta W star is this quantity here is going to be a bad approximation to the true delta W star. But delta W star lies entirely in this space. So the other thing we need, of course, is that delta W star lives in this space. Delta W star lives in the space in low D space. Okay. And now, so the data, the fact that the data lives in low D space and delta W star lives in low D space, so these things are a combination. The data is a combination of the distribution of our X news and the mapping from X nu to the high dimensional space. And remember that I never told you what the dimensionality of this one. This is so dimensionality of phi of X equals the number of weights. So that's huge, right? If we're not careful, we're going to massively overfit. Unless the data lies in low dimensional space. So now the network really matters. For some networks, this might hold. For other networks, it doesn't. Okay. And in the deep learning field, there's basically a huge, giant search for architectures, which means for phis for which these things hold. The data lives in low dimensions, and delta W lives in the same low dimensional space. Okay. And people are constantly coming up with new architectures, you know, there were convolutional neural networks, ResNets, you name it. Now there are transformers, and they're all a search to get these things to hold. And we don't really have any theory to guide us. We're just guessing. If you guess right, you win $1 trillion. You get super, super rich. If you guess wrong, well, you try again. Okay, so this, of course, so far we've been in the regime where we've Taylor expanded our Y. Now that actually doesn't, turns out that if you have a very small number of training examples, this is a good approximation. If you have a lot of training examples, which you typically have, it isn't a good approximation, and you quickly leave the space. So I'm going to tell you now, this is basically several things could happen. Okay. So one thing is for sure. So basically you can always Taylor expand. Okay. You can always Taylor expand. You can always write this down. And this is always going to hold for not too many training examples and a small learning rate. Okay. So the picture we should have is the following. So here's basically our weight space. Weight space. So this is our weight space. We're going to draw it in 2D. Yeah, this is, billion. It can easily be billion dimensional. Okay. And as we train, we start here at initial weights, and we move through, we wander through the weight space, and as we wander, our training error goes down, down, down. Now, in the neural tangent kernel regime, we understand everything, but that's because it's linear regression. But if we leave the neural tangent kernel regime, things change. So, but you can always pick any point, and we can, at this point, we can approximate f of W and X is approximately equal to f of W. I'm going to call this time t, where time is measured in epochs. This is WT, comma X plus delta W dot phi of X, where delta W is, W minus WT, and phi is the partial of F of WT, comma X with respect to WT. Okay. And so what we know is these overparameterized networks tend to work pretty well. And there are only a couple things that could happen, and we don't actually know which one it is. So first of all, so we'll say, this is t equals 0, and this is t equals, t final. And we don't, and so we can look at the sort of the covariance. So look at the data. Data, remember, is 5x. Data really lives in phi space, and it could be. So one possibility is basically initially your data is, combined to some low-d subspace. So a long covariance ellipsis means data is combined to low-d subspace, and maybe W star. I mean, sort of all sorts of possibilities. Like we'll write down the two. We'll write the two initial things that could happen, or it's not. And at T final, we have the same two possibilities. Could be. And we kind of don't know where we end up. There's also the issue of what's W star is. So we kind of know that we don't really know which path we take. Is it this? Is it this? Do we start here, end up here? This seems unlikely. Okay. Now, the reason it's possible that we can end up here is that you end up in a regime where small change in the weights don't matter, because remember at T equals T final, our model looks like T final F. Actually, I'll draw it over here. So at T final, or T final, F of W and X equals, well, near T final. Near T final. F of W and X equals F of W T final, comma X plus delta W dot phi, call it W T final. Okay, so it could be that this is a really good model, so it no longer matters if the data lies in low dimensions. Okay, this already fits the data really well. If you don't get that right, it doesn't matter. So that's why it might be possible to be here, and we don't really know the geometry of this. And if we do, it'd probably give a lot of insight. My guess is that we end up, this is what happened. We start off in low D manifold and we end up in low D manifold. And if we have the wrong network, this doesn't happen, we don't learn very well. So something like this, I would guess, would learn very poorly, and something like this would learn really well. Okay. But in any case, sort of the key take-home message is here. Ultimately, these overparameterized networks work is because the data, and the data is basically the initial data passed through, turns out, derivative of this function with respect to the weights. It's passed through this incredibly complicated nonlinearity. If you can do that and get the data to be line low dimensional, and the true sort of weight lies in the same low dimensional subspace, you're going to learn really well. If that never happens, you're not going to learn really well. And unfortunately, we have no theory of when that's going to happen. If we did, we'd have a much deeper understanding of deep networks. Okay, so that's the take-home message is really about these overparameterized systems. Even though they have a large number of parameters, it doesn't matter if the data lies in low enough dimensions, and they'll still work. And it turns out when you're building deep networks, there doesn't seem to be any limit yet. Bigger and bigger and bigger networks work better and better and better. And there must be some trade-off where eventually there'll be a trade-off. But it must be the case that the bigger networks give you flexibility without sacrificing this low dimensionality. And it's completely not understood how that happens. Okay. So we've been talking in some sense about abstracts and about these networks. What I want to do now is switch gears a little bit and consider some practical details. How do we train the networks? So remember, from a while ago, if we have a model y equals f of w comma x, and the loss doesn't have to be the squared loss, but it's sort of easy to understand. Sum on mu of y mu minus f of w comma x mu squared. So we want to update the weights by taking a derivative. So delta w, actually, delta w sort of has a different meaning now. So I'm going to do w on step t plus 1 minus w on step t equals partial of equals minus eta partial of L with respect to W. Okay, and as we saw earlier, that means that L of W t plus 1, so loss, remember, depends only on W now, minus L of W at time t equals L of WT plus WT plus 1 minus WT minus L of WT. And if the learning rate is small enough, if learning rate eta is very small, that means this quantity is very small as well, and you can Taylor expand. It's approximately equal to L of WT. This is actually WT here. L of WT plus minus eta, the partial of L minus eta respect to WT, sorry, dot WT plus 1 minus WT minus L of WT. And these two terms cancel. And for this term, we use this, and we get equals minus eta, the partial of L respect to WT, dot partial of L respect to WT. Okay, which is less than 0, less than or equal to 0. So it vanishes when the gradient vanishes, but it gets smaller and smaller in every step. Now, this is non-convex optimization. It doesn't mean we find a global minimum, but it does mean we find a local minimum. And empirically, all local minimums seem to work out about the same. So the problem, of course, is this is a complicated function. So how do we take a derivative of a very complicated function? And for that, we use a chain rule. We have a few minutes, so I'm going to derive it. I'll talk about it a little bit next time. Talk about the implications. So remember, our model is XL in layer L equals some nonlinearity of W L dot X L minus 1. And I call this thing HL. So HL equals W L dot X L minus 1. Okay. And I think it's actually easier if we use components. So I'll have X I L equals phi of the sum on J of W, actually with the sum on K of W I K L xk L minus 1. And HIL equals phi of equals the sum on k of W I k L x k L minus 1. So this thing equals phi of H I k. Okay. And now what we want to do is partial of L with respect to W I j layer L, and that equals a partial of L with respect to HI in layer L times the partial of HI in layer L with respect to X, sorry, with respect to W I j in layer L. And if you look over here, the derivative of H with respect to W, it just gives you an X. So this thing is equal to partial of L with respect to HI in layer L times xj in layer L minus 1. So really the thing we want to compute is this quantity, partial of L with respect to HIL. And we're going to, this is where we use backprop. We're going to write partial of L with respect to HIL is equal to sum on J of partial of L with respect to HI in layer L plus 1 Hj in layer L plus 1 times the partial of Hj in layer L plus 1 with respect to Hi in layer L. Okay. And that's actually easy. Hj L plus 1 equals the sum on K of W I K L plus 1 times XKL equals the sum on K of W I K L plus 1 phi of H. Okay. So we differentiate this quantity here with respect to HIL, we get equals the sum on J of partial of L with respect to HJL plus 1 times W I J L plus ready W I J L plus 1 times phi prime of H J L. Okay, and that's a famous backprop rule. It relates the loss or the derivative of the loss in this layer, derivative of the loss in the next layer. Okay. And that allows you to very, 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 very efficiently compute derivatives. That's what all these automatic differentiating programs do. So we're out of time. I'm going to stop here and to continue a little bit with backprop. I'll say a few more things about deep networks. I'll talk a little bit about transformers and unsupervised learning. And then we'll switch gears a little bit and talk about reinforcement learning, different kind of learning, and in particular application to decision making. Okay, so I'll be here for a few minutes if you guys have any questions. Otherwise, I'll see you next Monday. And I better save the photos before I forget. Okay, let's make sure that works. Voila. Okay, I guess that's it. Others.